Okay. So we have today Huang, who is third-year PhD student working with Josep Miguel Girard, and he will talk about magnetized envelopes in Orion.
Yeah.
Please go ahead.
Thank you for the introduction. For introducing me. I'm the third-year PhD student. Working with Josep Miguel, Chema, and Alvaro. And this is the title on the properties of magnetized envelopes in Orion. The scales for envelopes is from hundreds to thousands AU. So and I will follow the outline and first to give an introduction of the star formation background, and then I will and some mechanism related to this work, and then I will briefly introduce the ALMA observation and data reduction. The results and conclusions will be given in the end. So the first question has been on my mind is that how do stars form? First of all, where do they form? The stars actually form inside this molecular cloud, this dark lens, and these large structures full of dust and gas. And of course, this is not our galaxy. We have to move to the next slide and crash into the age one. This is a nice Gaia images of our galaxy, and you can again see the dark lens here, but now it's from our perspective on Earth. So the stars form inside this huge cloud, huge structures. Here is you can see the scale bar. This is scaled by the sort of nearby star forming regions. And here is Orion, one of our famous star forming region. But the star actually form individual objects from this arrow. So this is a multi-scale process. This is here is a scale-free picture. So there are so many questions that can be answered of the formation from the largest scale down to the smallest. On the upper left, here you have maybe maybe you have a piece or maybe actually dry molecular cloud, and then as you move down to the right, move clockwise down to the right, you have a molecular cloud, which is a dense region within a cloud, and then you get a protostellar core where one or maybe a few stars are going to be forming, and then down to the protoplanetary disk, and then the solar system, like our Earth, after all the dust and gas are blown away and more accreted. There are so many questions we can ask. What do these molecular clouds look like? How do they form the structure that we see? As it turns out, it's quite filamentary and elongated. And once you get down to the protostellar scale, how do these molecular these stars actually accrete their material? And what are the irradiation conditions of these protostellar cores? And for people who really care about the disk, what does the magnetic field look like? How strong is it? What is it doing inside the disk themselves? Because people have known theoretically for decades that magnetic field is essential for the formation of structure within disks. So to answer these questions, the polarization of magnetic field is central. So I would like to introduce a mechanism called radiative alignment torque, which will cause the dust grain align with the magnetic field. This is a multi-step process. If you shine light on, if you shine light on a regular grain, and the left-hand circular component and right-hand circular component of the light will cause the grain will scattered differently. That means the light the scat will cause the dust grain. That means the light will impact the torque to the on the grain and make it spin. So it is this transfer of the torque is efficient once the wavelength of the light less than the grain diameter. So if the dust grain is paramagnetic like silicates, the Barnett effect will cause the grain become magnetized. So this magnetization interacts with the external magnetic field, and over the continual radiative torque over the more Raman pulsation period, and cause the grain align with the magnetic field. So this theory predicts that the magnetic field align their long axis. This theory will predict that the irregular grain with paramagnetic property will align their long axis perpendicular to the ambient magnetic field. So you can see the cartoon field here, the cartoon grain which is aligned by the bead-red mechanism. So they can typically emit the polarization more strongly along their long axis than along their short axis. So you detect the polarization orientation, and to infer the magnetic field direction, you take this orientation and rotate it by 90 degrees. That's what we are going to see for most of the talk. Another mechanism could produce polarization is the self-scattering. This is independent of the magnetic field. So if you have an unpolarized line and hit a dust grain, and this light will be polarized depending on the angle where it is scattered. The steeper angle, it will be scattered, and the flatter angles, it will not. This is called Rayleigh scattering. The condition of this is the maximum grain size should be comparable to the wavelength. And in disk, here is the scattering do not come from the scattering doesn't come from the star, because the wavelength we observe is sub-millimeter or millimeter. Its emission is insignificant comparing with the star's luminosity. So instead, the self-scattering occurs. That is, the scattering of light from the dust grain hits another dust grain. This is self-scattering. So to achieve the polarization, you need to have an anisotropic radiation field. If you have an isotropic radiation field, that means the radiation comes from all the direction equally. So it's not, they will not produce the polarization. But if you in an anisotropic radiation field, that means the radiation have a preferred direction to hit this particular dust grain and to resulting in polarization. So in this case, the anisotropic radiation field is from the interior, and and the polarization we expected is right here. So after apply it to the entire disk, we have the polarization direction will be radial inside and azimuthal outside for the face on disk. And for the inclined disk, the polarization vector are parallel to the minor axis of the disk. So this is independent of this polarization caused by self-scattering is independent of the magnetic field. So for the role of magnetic field, have a look to the linear, let's say, integral convolution map from Planck correlation. The color scale here is the density, and the column density, and the drapery, string-like drapery indicates the magnetic field direction. So comparing the dust map with the magnetic field inferred from the dust polarization, we can magnetic field actually is doing something important at a large scale, the molecular cloud scale. So what I concluded was that the magnetic field in lower density gas is tend to be parallel to the preferentially structure. So you can see clear here the magnetic field along the preferentially structure in lower density gas, and while in dense region, magnetic field is tend to be perpendicular to the outflow. To the preferentially structure. So this suggests that the structure is formed by the gravitational collapse and along the field lines in dense region, and the string line material will along the relatively strong line in the dense region, in the lower density region. So the conclusion is that the magnetic field is dynamically important at a large scale. So what about at small scale, like from hundreds to thousands AU? Magnetic field always core magnetic field is always misaligned with the filament magnetic field. At core scale, magnetic field always shape hourglass structure due to jacking of the field line by infalling flux material. But many protostars core have a more complex morphology. So observationally, magnetic field is misaligned with the outflow, both in low mass and high mass star-forming region, which cannot be neglected at small scale. So different evolutionary stages, different star-forming conditions, and different observational spatial resolution can greatly affect the results of the magnetic field. So to study the role of magnetic field at small scale requires a survey of source in a single region that has typical star-forming conditions. Orion may be the best region to study the magnetic field at core scale because they have very different star-forming conditions, and it is the closest massive star-forming region. It is about just 400 parsec away from Earth, and it is a well-studied part of the large molecular cloud complex. It also has the largest population of the class 0, within 500 parsec. Most most sunlight star, including Sun, are found in the high mass star-forming region, making Orion a more typical representation of star-forming conditions within the galaxy. So after considering about points, the B-field Orion Protostellar Survey is proposed to observe 870 micron, which is a band 7 polarization survey, and toward 61 young protostars objects with a scale of 400 to 2000 AU. at these scales, magnetic field, the observation can chase the magnetic field uniformly around the protostar. So the observation was made with ALMA in 2019. The angular resolution is 1 arcsec, which refers to about 400 AU. And here is the continuous spectral zeta. 12CO and 322 and C17 322 are the main molecular lengths in this work. 12CO 322 chase the 12CO 322 chase the outflow structure, while C17 322 map the velocity field in dense gas because it is optically thin. And the data reduction was performed by in CASA 514, which is indeed divided into 3 parts. The first one is self-scattering, self-calibration to input the quality of images, and then we produce the dust continuum map and polarization map, which refers to the Stokes IQU. And the polarization intensity is the equalized by this formula and the polarization angle. And finally, we produce the image cubes to identify the outflow structure and the velocity field. So here's the results after data reduction. We have 17 sources with compact polarization emission. The color bar in the first column indicates the polarization intensity, so which is very compact. We also fit this region, and we find that the magnetic field, the polarization in this region are almost from the disk. So it may be produced by the self-scattering. This red vectors indicates the polarization, and this is the bullshit outflow, redshift outflow, and the contour is the total intensity contour. And the second column here is the velocity gradient, velocity field, and the redshift and bullshit outflow position angle. And the third column is the enlarged perspective, the second column. So you can clearly see that the polarization vector is almost along the outflow direction in this case. So after excluding these 17 sources, we have more complex, more extended polarized emission. So which is thought to be caused by the dust grain alignment chase the magnetic field. So here we can still see the polarization vector, but now for the second and third column, the black vectors is the magnetic field. We can see in this case have a hourglass shape, which is the magnetic field converge inward and expand outward. And for this, we can see the magnetic field is almost along the outflow axis. And for the rotated hourglass, which is the same, almost the same with the hourglass, but rotated by 90 degrees. So we can see the outflow is perpendicular to the outflow axis. And for the spiral, we also find the spiral. We have 9 sources of spiral morphology and 5 complex. Just have a look because it's hard to check today. And do not have enough data to identify the magnetic field morphology. We have 5 sources. So thanks sensible overall useful comments to produce this image. So we have a source with the magnetic field morphology of standard hourglass. 13 is rotated hourglass, and 9 is spiral pattern magnetic field. And also we find 16 self-scattering magnet case. To estimate the direction of outflow, we connect the source center with the edge of the redshift or blueshift outflow loop, and then take the bisector of the open angle. The redshift part and blueshift part as their position angle. And finally, we take the average of these two position angle as the outflow direction. So here the scale we use is 1000 AU because at this scale, most of the source have a clear outflow structure. And the polarization orientation, we first follow Chekhov's method to perform the total intensity weighted to give more weight to the position angle in higher density region. So Q and U here is the polarization component and linear polarization component, and the I is the total intensity, which is weighted by it. And we also perform a error weighted to give a more uniform weight for all the region. So this is the formula. In case of the if the polarization changes the magnetic field, we should rotate it by 90 degrees to infer the magnetic field direction. And the disorientation, because typical typical size of the disk is from 30 AU to 250 AU, which is unresolved in our observation. So we take it from the higher angular resolution observation of Tobin. So and the source with inclined angle less than 30 degrees are excluded because in these cases they are almost phase on, and the disorientation along the major axis will have a large uncertainty. So let's see the result. This is for the 17 compact polarization source. You can see the histogram. This is the outflow versus the polarization direction. We can see they are almost parallel. And for the right panel, we can see the disorientation versus polarization orientation, almost perpendicular. Note that this orientation is a major axis, so which is consistent with the self-scattering. So indicate that the grain size would be comparable to the wavelengths. And for the other 14 source, we have which is chase the magnetic field. We have about 40 of the source, 40% of the source show a perpendicular chain. But for the other source, it's almost randomly. And this is weighted by the intensity, which will, if you go to the inner region, they will have a more weight. It will be contaminated by the self-scattering. So for the right panel, we exclude the inner 400 region to avoid this effect. And the largest region is 1000 AU to give a more uniform, region for all of the source. So we could say we do not find any clear correlation between the outflow and B field, suggesting that magnetic field may not play an important role in setting the angular momentum of embedded envelopes and outflow. So for the angular momentum, as we mentioned just now, to obtain this information, we put the PV diagram. So here we choose this like a region of 400, inner 400 region of the redshift side and blueshift side. So the redshift side have a highest peak, highest intensity peak and correspond, and we can get a corresponding velocity value. And for the blueshift side, we also get a velocity value. And to calculate the absolute velocity gradient, this one may not be equal 0. So which indicates the rotation motion. But for the right, for this one, they have in this offset, the highest peak, they have the same velocity value, which indicates the absolute velocity gradient equals 0. That means in our observational spatial resolution, angular resolution, we could not say, we will say there may be some rotation and maybe dominated by the info motion. So we have 14 sources with envelope rotation value based on the observational angular resolution. So for these 14 sources, we to estimate the velocity gradient direction, we fit a 2D linear fit to the moment one map within 1000 AU. So we get we also have a direction of a velocity gradient, a direction of the outflow, and we divide this source into 3 parts. The PerpType, which is the velocity gradient perpendicular to the outflow, and RandType, which is the velocity gradient blending a line with the outflow, and the unresolved type, which is the velocity gradient is unresolved. That means the absolute velocity gradient equals 0. So first we can see the RandType source here. We have A source belong to the RandType, and now the position angle of magnetic field is weighted by error by its uncertainty. And we can see the blue one, the blue points, I would say. It indicates the source with clear, with reliable disorientation, while red points do not have reliable disorientation. And the green bands indicates the parallel. These two direction is parallel, and the yellow bands indicates the perpendicular. So we can see outflows, in this case, almost perpendicular to the magnetic field, and the Dix orientation almost aligned with the magnetic field. And for the RandType, we cannot see any change, maybe due to the small sample of the source. And for the unresolved type, we also cannot see. any correlation. So we plot the histogram again here, but now weighted by its uncertainty. So we have 38% of the source show a change that magnetic field perpendicular to the outflow. And this angle is weighted, it is obtained when the plane of the sky, which is 2D, but actually in space, it should be 3D. So we plot the to study the projection effect, the influence of projection effect. We plot the cumulative distribution function to compare our observational angle with the simulated angle. The simulated angle for parallel model is from 3D space, when the angle of 3D space randomly project into the 2D plane. So for the parallel case, have an angle of 0 to 22.5 degree, and random is 0 to 90, and perpendicular is 67.5 to 90. We run the case test to study if this observed distribution drawn from the model. We see for parallel cases, the case test probability is less than 0.1%, and for the random model is 0.3, and for the perpendicular case is 0.6. So both of random and perpendicular models could be possible for this observed distribution. The KS test cannot discern between these two cases. So let's see the summary again. In RandType, in unresolved type, at the standard hourglass have a source, and all the sources are in the unresolved type. And for the PerpType and RandType, we have a source in PerpType, 6 sources in RandType. This 14 source almost have a rotated hourglass or spiral hourglass. So come to the conclusion. For the cell scattering, we find 16 sources have a cell scattering. Most of them are class 0, except only one cases of class 1, indicating that grand growth has already occurred in the disk in the earlier stage of the protostellar phase. And the second, relative alignment between the outflow and magnetic field. The initial misalignment between magnetic field and the rotation axis will lead to less magnetic field breaking of the collapsing core, enabling a more easy formation of the disk. For the third B-field morphology, we see all the standard hourglass shape are in the unresolved type, probably because the magnetic field is strong enough to slow down the rotation rate. This refers to the magnetic braking. And most of the protostars with strong angular velocity gradient, which refers to PerpType and RandType, appear to have a rotated hourglass or spiral magnetic field morphology. And for the rotated hourglass magnetic field morphology, they have their magnetic field parallel to the velocity gradient and perpendicular to the outflow. So in this case, the gravity is strong, because the velocity gradient is almost indicates the collapsing direction. So the gravity is strong enough to bend the field lines appear perpendicular to the outflow axis. So final one is the field lines of the spiral morphology do not align with the both velocity gradient and outflow. In this case, the rotation is significant to twist the field lines and give rise to a helical pattern of the magnetic field. So I will stop here. Thank you for your attention.
Thank you for showing these nice results. Questions?
Thank you for a nice talk. So you mentioned about polarization due to self-scattering. So it's like a thermal emission which is polarized, right?
Sorry.
So basically, if I understood correctly, it is a thermal emission that can be polarized.
Yeah.
So what is the typical behavior of polarization? Like, is it like linearly polarized or thermally polarized?
Well, the question is about polarization different.
For the self-scattering. Okay.
Yeah.
And so the question is,
like, is it like, what is the typical behavior of polarization for self-scattering? Like, is it?
I see. So for the property of the self-scattering, right? The question is that the property of the self-scattering. We can see from the observation, we almost observe the incorrect disk. So the polarization pattern is always perpendicular to the minor along the minor axis of the disk. So this is the case. This is the property that we have observed in the observation. So
some specific parameters differentiate it from the emission that is non-thermal?
I don't think so, because the scattering of light, if it is polarized, it will have a steeper angle you observe. And if it is in a flatter angle you observe, it will not. It will not have a polarization signature.
More questions?
Yeah, okay. I wasn't sure if there was someone behind this. Thanks, Bob, for the talk. So one question about the rotated hourglass morphology. So you say that it's gravity that it's pushing the magnetic field lines.
Yeah.
But so at the same time you have the outflow, right? That it's going in the other direction.
Yeah.
So how do you put together these two things, that you have the outflow that it's pushing material away, but then you say that gravity is pinching the magnetic field line?
Yes, that's a good question. Because we need the velocity gradient information. So because the velocity gradient almost indicates the material, the collapsing direction. So in this case, if the field lies along the how to say, the direction of velocity gradient, there will be that the gravity would be significant enough, and maybe the outflow will influence the alignment of the magnetic field. But in this case, in some cases, we also see in some cases that would be affected by the streamer, like maybe the accretion streamer or maybe the outflow cavity wall. We don't know because we don't have enough angular resolution to do it.
Thank you.
You're welcome.
More questions? I have a quick question. So you said basically you cannot. You are not sure you can make a distinction between random direction and perpendicular direction, right?
Of what?
Of magnetic fields in one of the cases you showed. Statistically, you cannot distinguish in one of your last slides. You showed statistically you cannot distinguish between random and perpendicular direction.
Yes.
But which physical mechanism do you think it's more likely to be at work here?
I
Because there should be two different physical mechanisms.
Yeah. So for these things, so we have for PerpType source and RandType source, right? The PerpType source we have already applied the chain. This case, the magnetic field is along the how to say, magnetic field is along the outflow, perpendicular to the outflow and also along the velocity gradient, right? So that's the strong correlation that we see. But for the RandType, we do not see any correlation. That's what I say. And for this one, the velocity gradient is strong enough because we have already calculated the absolute velocity gradient. And for this case, in this case, rotated hourglass, which is the magnetic field along the velocity gradient direction, while spiral is not. So I think, can I answer your question?
Yeah. So my question is, you partially answered in the sense that I wanted to go in the direction to say that morphology doesn't necessarily mean a physical mechanism at play. I mean, it's just one aspect of what you're observing, right? But it's possible that you have different mechanisms at play in different cases of morphology. Because you have random types both in spiral and rotated hourglass, for instance.
Then the type what? They have four.
Yeah.
Right?
Yeah. Here you have one. Yeah. Okay. Statistically, it is less significant, but still something. Still non-zero.
Yeah, I think so. I agree with you.
Okay. More questions? So let's thank Bo again.
Thank you. Is there any questions? No.
Yeah, here there is also an online audience that I completely forgot about because I couldn't hear anything from here. Okay, I think we can